Good morning, Noel, and welcome to the third appointment with this series of webinars dedicated to simulation apps. We do believe in this very interesting technology, and most of all, we think it will be part of the future of concepts like simulation governance and simulation democratization. The previous two webinars were focused on giving an introduction about what are smart engineering simulation, webinar 1, and an exploration on functional and technical requirements for sim apps during the webinar 2. Both of those webinars can be reviewed just clicking on the YouTube link in the website www.enginesoft.com/ESRD. Now, I am very happy, and it's really a pleasure for me and for ENGINESOFT hosting our partner ESRD, and in particular Mr. Riccardo Actis, CEO of ESRD, for this series of webinars. Riccardo today will go through topics like select, create, test, and deploy simulation apps. Next appointment held in September, where we close the series with examples and reference case studies. Thank you.
Thank you, Luca, for the introduction. Good afternoon, everyone, and welcome to Webinar 3, Creation, Testing, and Deployment of Simulation Apps. Before we get started with today's topic, I would like to do a brief introduction or review of the topic that we covered in Webinars 1 and 2. Webinar 1, we reviewed the reasons why simulation has historically been performed by specialists and why legacy FEA methods struggle with standardizing and automating simulation processes. We look at what are simulation apps, CMAS for short, what are the benefits, and what are the challenges to creating and using them. Webinar 2 is for the deployment and development of smart simulation apps. Webinar replays, as Luca mentions, are available as YouTube videos, and you can find them in the links that are indicated in this slide. One other aspect that we covered in detail during the Webinar 2 was what do a smart simulation app require? And what we addressed at the time was the fact that across the simulation functions, and that include knowledge capture, modeling, prediction, process automation, the technology foundation used by simulation app should be simple and standard, accurate and complete, correct in all details, fast and efficient, achieve the goals with minimum effort, robust and reliable, where trusted results are available for our users. If they meet these requirements, then they are what we consider smart engineering simulation apps. Today, we are going to address industry-specific portfolio of simulation apps from new generation of simulation tools for an analyst and design engineer to fit into existing analysis process. We're going to review the enabled FEA technology for the creation and deployment of simulation apps, and the systematic approach for selection, creation, testing, and deployment of simulation apps. An example of simulation app created in a digital e-handbook. This figure shows a typical portfolio of simulation apps, and the deployment mechanism is such that when one is selected, like in this case it's highlighted in red, the document is displayed indicating the function or the reason for this simulation. Once this is selected, the model is loaded into an easy-to-use interface. The mesh either is automatically added to it after the user enters the input, or it is pre-existing and changes with the changing topology, and solutions are obtained and deployed and reported to the user, who does not have to know anything about finite analysis in order to be effectively using them. A few words about our company. Engineering Software Research and Development was founded in 1989 and we have headquarters in St. Louis, Missouri. We focus exclusively on computer-aided engineering, and reliability to simulation governance is our main focus. That means verification through estimation and control of the error of approximation, and this we do through hierarchy finite spaces, validation through estimation and control of the errors associated with the selection of mathematical models, and for this we develop a hierarchy modeling framework that I will refer to a little later, and standardization through knowledge capture and simplicity in deployment. We produce engineering software for numerical simulation in the field of computational solid mechanics. We have been focusing primarily in aerospace and defense applications until recently, and smart engineering simulation for the industries have been one of the areas in which we have invested time and effort. More information is available in our website. What are our software offerings? Smart engineering simulation apps, or SISA for short, are engineering analysis tools that are developed under contract and for private licensing to industrial customers. Then we have commercial analysis products. The three that are listed here: Stress Check Professional is an advanced numerical simulation tool for FEA experts. CAE-Handbook is a customizable FEA solution for non-FEA experts. It provides a framework for repository of final element analysis type solutions that can be developed by a specialist. And a Stress Toolbox, which is a specialized desktop application for non-FEA experts that targets larger and more complicated problems to be solved in an automatic way. And finally, we offer FEA software technology for licenses for embedded private level development of simulation apps. Regarding services and projects, industry-specific solutions from a new generation of simulation tools for both analysts and designers. That includes portfolio simulation apps for detailed stresses, composite analysis, fracture mechanics, repairs, global local, and others that have a built-in quality assurance dashboard. And we will see what that means in a moment. The Handbook solution for industry to capture their institutional knowledge and best practices. And we also do R&D projects to support the development and creation of design rules for new products. The technology base that supports the creation of these smart simulation apps was developed for high definition detailed stress analysis and for standardization of recurring analysis tasks as a goal, and was created for stress analysts as well as strength engineers. The technology base we have produced published documentation to support to describe exactly what is that we do. This is one example of an article of 2012 on simulation governance, what are the technical requirements for mechanical design, which is the foundation for the safe deployment of simulation apps. Also, there is a book in finite analysis that was authored by two of the founders of our company, and this appeared in 2011. Regarding the implementation, finite analysis that provides extraction of any engineering quantity of interest from any location in the model on the fly with convergent information. And to illustrate what this convergence information means, consider the case shown here in which we have a graph showing the maximum principal stress in a component as a function of the number of degrees of freedom. These degrees of freedoms are increased systematically on the fixed mesh that you see on the screen by using a hierarchy finite spaces. And what this graph indicates to the end user is that as the number of degrees of freedom is increased, the quantity of interest, in this case the principal stress, remains practically independent of the number of equations that have been solved, providing feedback information on the conversion characteristic of the solution. As I mentioned earlier, this FEA technology is based on a hierarchy modeling framework and hierarchy finite spaces that allow us to have extremely simple element library, and where there is no need to search for the right elements and exact geometry representation to reduce the approximation error associated with the representation of the solution domain. High resolution results are obtainable from low density meshes. Continuous non-nodal solutions are available throughout the model, which allows the user to investigate results anywhere in the model, through a live post-processing function, which allows any function anywhere and anytime to be result to be produced. And it provides, of course, automatic objective measure of accuracy, as we demonstrated in the previous slide. This is the only FEA implementation existing in the market today, which was designed to support verification and validation to enable the practice of simulation governance. An example of simulation app in a FEA-Toolbox, one of the products I mentioned was a stress check toolbox, which is a way to deploy FEA-based tools for the analysis of structural details with easy-to-use interfaces, while giving analysts confidence in the computed data by providing convergence information. In particular, we take the case of the multi-fastener analysis tool. This computes accurate fastener loads for single, double shear joints with any number of fasteners by performing contact analysis. What this does is enable both seasoned analysts and junior engineers to perform the same quality work using a tool that provides the quality information and the assessment of the quality. In the case of the CAE-Handbook, this is ideally suited to deploy solutions of classes of problems that are topologically similar but can be changed by parameters that control the dimensions of the object. To have material property can be assigned. In this particular case, we are looking at a pie joint, which is a typical detail in composite materials. If we zoom in into the regions of interest, what you will notice is that there is a ply-by-ply modeling in which each layer is represented by an element. These elements can tolerate extremely high aspect ratios. Once the user adopts the parameters that control the play layout, the stacking sequence, the material properties, and the dimensions, and the loading on this component, they can solve to obtain the results of interest. This reduces substantially the time required to analyze this type of joints, which are essential for of flight. Let's now concentrate on the move to the second part of the presentation, which is the creation of simulation apps. In particularly, we're going to review the process of selection, creation, verification, and deployment of simulation apps. So the process simply consists of these 4 steps. Select the problem. That means identify clearly the customer need for a problem class, and then proceed to the creation of the app by first working on the technical requirements and decided which solution will provide the implementation for those technical requirements. Once the app has been created, there is a verification step where the proposed solution is tested and verified. And finally, the deployment mechanism is introduced in order to make it available to customer side. We are going to illustrate the that was it's a simplification of a real case that we have performed just to illustrate the basic ideas. The customer problem was in a standard process that they have in which the idea of computing the maximum stress is critical from the point of view of fatigue, or the situation in which plate with countersink holes where the target was consisted on what is called as KT compounding. For those of you that may not be familiar with this terminology, what it means is that the solution of the maximum stress is obtained by superposition of simplified cases as we will illustrate in a second. The idea, the first task is identifying the relevant parameter for the case. We just showing a few that are relevant, like the fastener, the hole spacing, the plate width, the diameter of the hole, the edge distance, the thickness, countersink angle, and others. The standard process basically can be summarized in these few steps. Given the material properties, dimensions, and loads, the goal is to compute the gross stress coming from the loading, assuming that there is no holes, then introduce the geometric effects, the two-dimensional geometric effect like hole spacing, edge distance, plate width effects to compute a KT through, that means the stress concentration factor that has to be applied to the through load. Finally, a correction term is added to account for the three-dimensional the countersink and combine them to obtain the maximum stress. The part of the process that was identified by the customer as being problematic was the one indicated here, because of the procedure that we are going to describe in a moment was very prone to, was very operator dependent, the outcome of the result. The standard process was based on lookup tables and graphs. I'm showing here some standard information available in the literature. This particular customer had their own proprietary information to do this work. But basically the idea is that given the gross stress, a stress concentration factor for two geometrical effects were obtained from curves similar to this one, in which the user had to actually enter information and read from graphs, or maybe that sometimes they are computerized, but nevertheless they are interpolation on existing curves. Once these values obtained, for example, in this case 3 or 4 for a particular set of input, the second step consists in finding a stress concentration correction factor for 3 dimensions. Again, this was done using a proprietary set of data generated by the customer, and the number comes out of that. And the process consists at the end of multiplying the factors. So this is a typical terminology, which is an important consideration that whenever an application is developed to fit into a process, has to use terminology which is consistent with the way the customer has done it traditionally. In this case, the KT sigma through is obtained by multiplying the stress concentration factors for 2D and 3D effects with the stress, and gives a number at the end, which is the quantity of interest. When this was understood and clearly defined, the creation of the app was possible, and the method of implementation was the CAE-Handbook, in which a model was added to the library. And basically the process is very simple: select a model from the library, update the values, and solve for the maximum principal stress. This is in the diagrammatic form on the top. You can see a sketch of the model with the parameters to control, a box that allows the user to change the parameters, which has controls to make sure that the values entered are valid, and the output, the outcome of the result. The verification of the app was performed, taking a few typical cases that the customer has good reference, that they were sure that the process was done correctly with the standard procedure. The CAE-Handbook approach provided the value 7215 for that case. the compounding, the standard procedure, 73.88, a difference of 2%. So there was very good correlation between classical solution using KT compounding and the direct 3D FEA with CAE-Handbook, significant time reduction using CAE-Handbook, and accurate results that were supported for solution verification was the outcome. The deployment was done through the CAE-Handbook. The new model was added to the library. They have several models that were created for their needs. As the model was selected, a document indicating exactly the goal of the analysis, what was done, what are the boundary conditions, all the requirements to make sure that the end user understands what the goal of this problem is. Once the model is loaded and the parameters are adjusted, the only option for the user is to solve. The solution provides an automatic report, and it presents the result to the user in graphical form and also in color plots and in a window that can be manipulated and reviewed by the user. And of course, the information that is essential to make this deployment safe is to have a dashboard to provide quality assurance information for the convergence of the results of interest. In summary, the updated process solves a 3D elasticity problem, replaces a standard process of KT compounding that required several steps, and thus the solution became operator independent and consistent results with assessment of quality was produced. The standard process, on the other hand, was prone to error. Lookup tables or graphs used for determining intermediate results, interpolation often needed to find individual KTs, and the results were problematic because they're operator dependent. More seasoned engineers will know better how to apply this process. The younger engineer coming to the team, and that was a problem that this application solved. Here I would like to summarize the main technology differentiator for simulation apps that we offer. First of all, and essentially and very critical, is that solution verification with automatic quality assurance is an inherent capability of the implementation. Direct accurate geometric model is very important for this detailed stress analysis problem. We keep the idealization separate from the approximation, which allows simple and minimum element library to be used to just capture the topology. Therefore, there are simple meshes to construct, check, revise, and use for simulation apps with the speed up the process of creation. The implementation is such with the hierarchy Feynman spaces, and the accurate geometric modeling allows it make it feasible to use solid elements throughout, and thus removing one of the main obstacles in the deployment of simulation app by traditional Feynman implementation, which requires different element types, would make the deployment for non-experts extremely difficult. High fidelity multi-scale analysis on the same mesh are possible with this implementation in such a way that the same model can be used for both obtaining the structural response and the strength response on the same mesh. High fidelity results from low resolution meshes means that the mesh is no longer the main player in the definition of the approximation, but actually the combination of mesh and space used for the approximation is what defines the quality of the approximation. Continuous solutions are provided throughout the model, not just nodal, which make extraction of any engineering quantity of interest much simpler and robust. And of course, this ability to perform live dynamic post-process of results allow also changes that do not break the model or void assumptions, and provide objective measure of quality without an expert on call. This is one of the essential requirements for deployment of simulation apps. Without the onboard quality assurance procedures is very difficult to deploy or impossible because they does not, in general, is not qualified to determine for something may be wrong. So, as a concluding remark, the role of simulation app. Engineering simulation apps provide a framework for the preservation and accumulation of institutional knowledge. This is true for specialists and non-experts alike. They are designed to fit into existing analysis process. They capture the best practices of an organization, produce consistent results through approved procedures, remove operator dependence, and increase productivity. The benefits is that they make difficult classes of simulation problems easier, more accurate, and faster to solve by the specialists to support increasing complexity of products and demanding design cycles. At the same time, they make routine classes of problems, design problems, solvable by designers and engineers, as they did for years when using handbooks and design curves produced by methods groups. And the third group that it targets is empowering new engineers that join an organization to be productive sooner with access to reliable tools that have captured the institutional knowledge and best practice of the organization. If you need help with simulation app idea, please visit us at www.esrd.com. You can contact me and the information given here, or you can speak directly to the sponsor of this webinar series, EngineSoft, at www.enginesoft.com. And with that, I would like to thank you for your attention and open the floor for any question that you might have.
Thank you very much, Ricardo. Very, very interesting presentation and complete presentation with the and what I got beside all the concepts you explain is behind this technology there's a real change in culture regarding the FEM approach from engineer as well as from non-specialists, so design engineers. Ricardo, again, thank you very much, and thank you to all of you for your participation. I would like just to remind that in some days you will be able to review this webinar going to the web page dedicated to this technology. And of course, the next appointment on 8th of September, just after the holiday, let's say, with the last webinar of this series. Ricardo will show us some examples and reference cases about simulation apps using CAE-Handbook and Stress Check Toolbox. Thanks again, and see you soon.